All right, let's get into it. Today, we are unpacking some absolutely fascinating stuff from the world of biostatistics. We're talking about incredible AI that can literally read our biological age, some hidden viral threats that might be lurking in our own bodies, and the immense pressures on the scientists who are actually making all of this happen.
You know, this quote, it really hits on something important because behind every single one of these groundbreaking studies, behind every data point, you've got these brilliant researchers. And right now, a lot of them are dealing with a system that feels like it's valuing metrics way more than their actual mission.
So that's where we're going to start, with the human element. We're going to pull back the curtain a little bit on the intense and often totally unseen pressure that the very people making these world-changing discoveries are up against.
And here's the core of the problem. Instead of being free to follow their curiosity, to chase down those big, game-changing ideas, a lot of young academics are just stuck in this cycle of hitting administrative targets. And what that system can do, without even meaning to, is just stifle the creativity and independence that real scientific discovery absolutely depends on.
But what's so amazing is that even with all those challenges, the science that's coming out is, well, it's mind-blowing. So now let's pivot and look at two huge studies that are decoding our health in ways we really never thought were possible.
So check this out. These two studies, both from the journal Nature Medicine, are kind of like two sides of the same coin. On one side, you have an AI that's trying to predict our biological future. And on the other, a discovery that uncovers this ghost from our past that could be shaping our cognitive health decades down the road.
Okay, first up, the AI life clock. Before we even get into what it is, we have to talk about the scale here. This wasn't some small study. No, this model was built using the electronic health records from almost 10 million people. I mean, just think about that. The sheer volume of data is just staggering.
So what is this life clock? Well, think of it less like a calendar and more like a biological odometer for your body. It uses this really advanced AI to comb through health data and figure out your biological age, which it turns out is a much better predictor of your health than just the number of birthdays you've had.
And here's where it gets really fascinating. The life clock found that we basically have two different aging modes. Before you turn 18, your body's mostly in a development phase. But then, right after 18, a decline clock seems to take over. This is actually the first time any model has been able to map our entire lifespan, from being a baby to old age, into one single framework. It's pretty incredible.
Now, if you thought 10 million was a big number, get ready for this. For our second study, researchers analyzed the health records of over 100 million people. Yeah, over 100 million. And they were looking for a very specific and pretty startling connection.
And here it is, the varicella-zoster virus, or VZV. You know, the same exact virus that gives us chickenpox when we're kids and can come back as shingles when we're adults, is now significantly linked to a higher risk of dementia, especially Alzheimer's. It's like the ghost in our machine might be a virus we got when we were 5.
I mean, the implications of this are just huge. This research basically reframes shingles. It's not just a painful skin condition anymore, it might actually be a trigger for neurodegenerative disease. And what's so exciting about that is it opens up brand new and maybe even preventable ways to start tackling dementia.
So you're probably wondering, how in the world do they even do this stuff, right? Well, behind these massive data sets and these incredibly complex findings, there's this powerful and constantly evolving toolkit that modern researchers are using every single day.
A ton of this work is built on the shoulders of giants. And one of those giants is a piece of software called NumPy. It is the absolute bedrock of doing science with the Python programming language. It's so important, so fundamental, that it got its own dedicated review paper in the journal Nature. That's almost unheard of for a software library.
But it's not a one-size-fits-all situation, you know? It's all about picking the right tool for the job. Take something called causal analysis, which is basically just trying to figure out if one thing truly causes another. If you're using the R programming language, you've got a whole menu of options. A simple analysis, you might use the mediation package. Something way more complex, with variables you can't even see directly, you'd probably reach for something powerful like BRMS. There's a tool for every question.
So what about having to sort through that literal mountain of existing research papers? I mean, it's a total nightmare. That's where a tool like Covidence is a lifesaver. It just streamlines that entire process, turning this chaotic mess of screening papers and pulling out data into a clean, simple workflow.
And really, at the end of the day, so much of this is about working smarter, not harder. A package like Jeet Summary can take the super complex statistical output from a dozen different models and boom, instantly turn it into a beautiful publication-ready table. This saves just so many hours, which lets scientists actually focus on the science, not on the formatting.
So, how does this all tie together? Well, these researchers and their amazing tools, they don't exist in a bubble. They're all part of this massive collaborative ecosystem of shared data and open knowledge. And that ecosystem is what's really fueling the next huge wave of scientific discovery.
And this right here, this is what that ecosystem looks like. It's being fueled by huge open data sets like the Northwestern ICU database and the All of Us project, which basically invite researchers from all over the world to dive in. It's guided by open knowledge, like essential textbooks that teach these complex methods. And it's kept alive by open information streams, like RSS feeds that help scientists keep up with everything.
Which, of course, all leads to this final, really exciting question. We've got brilliant people, we have more data than at any point in human history, and we have smarter and smarter tools to make sense of it all. This combination isn't just changing science, it's putting it on hyperdrive. So the only question left is, what mystery are we going to solve next?